Hello, Professor. I had a question.
Good morning. What's the question?
Good morning. Initially, so like I was going through like the chapter that we were doing, chapter 5, essentially like complex numbers. Yeah. So like there was this definition of
Yeah, okay.
5
Can we talk about this at the end?
Oh, absolutely, sure. Yeah.
Okay, thank you. Yes. All right. Any administrative stuff? If you have something you want to talk about. For math stuff, yeah, let's talk about it at the end, because we have to go through this stuff. All right, so finally, let's start on vector spaces. What they are, what are some examples? These are sections 1.1, 1.2, and 5.1, or sorry, 5.2. So here they do real vector space that we're going to talk about. Here they do subspace, and here they do vector space over arbitrary field. So that's the outline. So I put in the thing we talked about from last time. So here are the axioms for the field. Again, we should think about this as the reals or complex numbers. So you have some number system that you're working with to do a linear algebra. E to the I pi 4, 6, I plus 3. And he had some axioms that we will keep coming to as we talk about the vector space axioms. Okay, so as you go into reading vector spaces, have somewhere on the side the axioms for the field. Are we expected to memorize these axioms? Well, I mean, that's a little bit of a tricky question. For the vector space, yes, because we, as you saw in the homework, we put some questions there where we ask you to disprove that something is a vector space or something is a vector space. So especially for disproving it, it's good to memorize a few of them that keep showing up, which we will go over. We will go over some non-examples. Is that okay, Rudrash? There will be some axioms that keep showing up. Okay. All right. All right, let's start with vector spaces. So the standard example is the one from 2 to 3 of Rn. So let me quickly say it on the side. So remember, Rn are all the vectors of the form x1 to xn, where xi is in the real numbers, right? So R3 was something like this. So this is the standard example for the vector space that we're going to use. So what's a vector space? Where it's a set and it's equipped with two operations, addition and scalar multiplication. Now, let's right away go up and compare this to the field. Here we also have addition, but we have full multiplication. So here you can multiply two complex numbers, right? 2, 3i. This makes sense, like 2 plus so on, by distributivity. Right, so you can multiply two elements of the field, but here we don't assume that. So, and you know that for Rn, like it doesn't make sense to multiply 1, 1 and 2, 2. That makes no sense. But you can take dot product. You can take dot product, and this is 2 times 1 plus 2 times 1, but this is now a real number. This is not a vector, right? So there is no vector multiplication. There's dot product, but there's no such thing as a multiplication that gives you some other vector AB, right? I see some questions here. Let me go through them. Sorry, Prof, but what is the 0f again? What does it mean? Right, as Angela says, yeah, it's the 0 as defined on that field. So let's go up. So 0f for reals is 0. For complex numbers is 0 plus 0i. For Rn, because Rn itself can be a field, but we're not going to go over that. It's the 0 vector and so on. Is that okay, Kellyanne? Did Angela and I help you with this? Is that okay? All right, so, okay. So there's no multiplication between vectors. Okay, so we have, oh yeah, and then I don't know what I'm talking about here. Not Rn, never mind. Just these two guys, C and R, yeah. All right, okay, let's keep going. So there is no vector multiplication. Okay, there is scalar multiplication and addition, but there's no vector multiplication. All right, first axiom, you need closure under the addition and scalar multiplication. Again, this is also in the field, so also in fields. What else to say here? Yeah, so for Rn, right? If you add two vectors, you get another vector component-wise, right? And if you further multiply the vector, like let's say 1, 2, then the multiplication becomes component-wise. So you get another vector. So those operations give you other vectors. What's an example of not being able to do that? Well, take something like V to be all the X, Y in R2, such that X is positive and Y is positive, right? Like 1, 1 is an element of this guy. Well, if you multiply by minus 1, 1, 1, you get minus 1, minus 1, which is not in V. So V is not a vector space. Okay. Can a field contain vectors or is it only numbers? It's only you need because you don't have vector multiplications. Yeah, so that means this array I should have said to be a field. So no, vectors cannot be fields because there's no way of multiplying them. Where it says addition, should it be V plus V? No, you should think about this as Cartesian product. So this notation here, that's a good question. Let's explain it. So this means that the input, so this is a function of VW. And what it does, it adds them. So it has two inputs. So this is a Cartesian product. Like R2, like f of VW is equal, let's say 1, 1, 0, 1. This is 1, 1 plus 0, 1. So 1, 2. Is that okay? Okay, good. Yeah, like we draw it. It's good. All right, so we need closure under addition and multiplication. We need them to commute. I have some non-examples at the end that we can talk about. But like yeah, so we when you have a matrix, when you have two matrices, we're gonna go over this example later. Something like that. You want to be able to swap the operation, like you're adding two data sets or something, or you're adding two vectors. You don't want to be getting different inputs depending on how you add them. So this is more like a physical thing. It comes from physics, but because there are non-commutative things. So commutative groups stuff. So for all these axioms, if you drop them, there are objects out there. But this is like the ideal object where you have everything you could wish for. This is a bucket list. All right. Associativity again. Again, it's a sanity check. So it sort of says that if you multiply the first two vectors is the same as, adding the first two vectors is the same as adding them in a different order. Right? That's okay, right? I'm still finding it hard to understand what a field is, what type of values can it P in the set of the field. Well, I mean, this is very general, right? Like we want to give you, we want to have the freedom to put any field we like. But if you see in the previous class, the most common ones are reals, complex, quaternions. Some people also take ratios of functions, ratios of polynomials. So there's a whole zoo, but the main thing that we're gonna cover are the first two. Okay, is that okay? So the mainly reals and complex for this course, but it can be very general. Why is it plus W? Because um, because it changes, right? So so you see, like for vectors, plus W means component addition. So you add them component wise. For matrices, something like that, I don't know. It means entry addition. I mean, I'm gonna do these examples in detail, but since you guys are just to get you going. So this is entry addition. This is component addition. So you each time it changes. Is that okay? So Kellyanne, was that okay? And Mayma, is this okay? All right. Field is essentially yes. Mayma, is that okay? Yeah, it could be vector addition. It could be if you could also have sets in the field. Well, the problem is, how do you multiply sets? If you find a consistent definition of multiplying sets, then yes, but that's the biggest obstacle. Addition is easy, right? Even for Rn, you have addition, but for multiplication is a big problem. Yeah, it's vector addition, but I'm going to do some general examples where it's not always vector addition. We'll come back to it. All right, distributivity, again, this is a sanity check, right? So you have 1 plus 3 times 1, 0. Then this is 1, 0 plus 3, 0. And it's the same as if you started like this. So this is something that we often have. It's not hard. Okay, this stuff is something that often gives non-examples. So additive identity and multiplicative identity. So for Rn, 0f is just taken to be the zero vector. Okay, so every component has 0. We were going to talk about it next. For matrices, sorry, this is a 0v. For matrices, we just take the 0 matrix. So that's the additive element. I mean, I'm gonna go over this in detail, but I'm just. And multiplicative identity, you always take the one from the underlying field. Okay. Now, what could fail is the way you define multiplication, and I will do an example. But at least for Rn, right? All it says is that 1 times 1, 2, 3 is indeed equal to 1, 2, 3. So just because you multiply by 1 doesn't mean you change the vector. You get the same vector. Okay. Okay. So, and yeah, I'm gonna do a non-example. So a non-example is take something like x, y in R2, but force them to not contain 0, like x plus y to be 1. Then 0, 0 is not in W, so W is not a vector space. Okay. All right. Because 0 plus 0 cannot equal 1. Is that okay? So, yeah. All right. What else? Yeah, and finally you have the additive inverse. So that means for every vector, you can find another vector or another vector. When you add them, you get the zero element. So let's do it for Rn. So suppose you have AB, this is V, then for minus V defined as minus A minus B, when you add them together, what do you get? You get A, B, then vector addition, so A minus A, B minus B. And so you get, here you use that there's an additive inverse for the field, right? So you know that these are the additive inverses from F. So again, let me go up just to remind you what was the situation in the field. Over here. So for the field, we know that every element has an additive inverse. Okay, so if given A, there is a minus A, so that when you add them together, you get the zero element of the field. So coming back to our example for Rn, where is it? We know that this element exists. I mean, for this example of the Rn, we know that we can find components that are additive inverses because we know they exist for the field. So when you add them component-wise, you indeed get your zero elements. Is that okay? 0 is in W, 0 plus 1. I'm not sure what the question is, Ismail. Can we have a vector space without the notion of distance, a metric? There's no metric here. Like for matrices, right? I mean, for matrices, there is a metric. Yeah, we'll do an example soon where there is no nice metric. Average 0f 0f would be the 0v for the space, right? Right, yeah, so exactly. So for this example, right? For this, in fact, let me generalize it. I mean, all I'm talking about here is Fn. So you have a field and you take it to some power n, okay? Like Rn, Cn, and so on. And indeed, when you add them together, you get 0v. Okay, average. What was the question of Ismail? I'm not, okay. Okay. Yeah, 0 plus 1 is 1. Did I make a typo or something? All right. Maybe you're talking about this. Yeah, this is not well defined, if that's what you mean. How would you visualize a field n since it's simple numbers? Exactly like this. So you have R3, right? So here you can have F, F, and F. And if you take an element, it will be A, B, C. So if it is if it's complex numbers, for example, like C3, let's say take C3. Of course, you cannot visualize C3, but you can think of it as a number system, same way. And if you take an element, it will be of the form, A plus IB, C plus ID, E plus IF. And this is like the, the A plus IB. This is the C plus ID. And let's pretend it's like here, E plus IF. Okay, is that okay? So you can pretend that it's like the real numbers. It's a number system. Okay. So is the multiplicative identity part of the field, but not the vector space? Is one scalar? Yes, exactly. So because we do not have, that's a very good question. So we do not have vector multiplication. So there is no 1v. There is no such thing as 1v because there is no vector multiplication. Yeah, like I wrote it. So it would be this like n-dimensional thing, right? So if n is 3, you will have 3 coordinates. Okay. I mean, of course, even for C3, right? What I wrote here is slightly like sleight of hand because A plus IB cannot be ordered linearly. So A plus IB is not ordered linearly, right? So this is like a sleight of hand. So you can't really visualize it. But if you want to talk about in proofs, then you can think of it like this, that every coordinate comes from your number system. Yeah, it is a vector. Yeah, this is a vector in C3. This is a vector of the fields, of the elements of the field. This is in F3. And here we take F to be, C. No, you can have, you can have vectors of the field, but you cannot have vectors as a field. So you cannot have F to be Rn. So that doesn't make sense, but you can have F of n to be a vector space. Yeah, good. All right, good. Now let's also talk about subspace. We're gonna talk about it more on Friday and tomorrow a little bit, but just to know what the definition is. So you start with some vector space, say like R3, and then you have some subset, let's say like W is R. Then if, well, you know what, W is R. Then if, what is it? If this W also satisfies the axioms of the vector space, then we call it W to be a subspace. So you can check that W is a subspace, W equal to R2 is a subspace of V. So these are both subspaces of R3. Okay. So then is it the case that the Cartesian product of fields is what produces a vector space? Yes, that's exactly right. So F of n is just the Cartesian product of n. Yep. So yeah, this is the picture, right? So each one of these planes gives you a subspace of R3. A non-example is take the one I mentioned before, take xy to be in R2 of x plus y to be 1. This guy is inside R2, which is a vector space, but W is not a vector space because, for example, 0, 0 is not in W. So W is not a subspace. It doesn't contain the 0 element. Will dimension of W always be? Yeah, exactly. So, and I think we're gonna prove that later on when we talk about bases. So I will leave that for later, but exactly, the dimension is always less. But we can do, we will do this more formally later when we talk about bases. All right, moving down. Right, so here I list a bunch of examples and then I'm gonna go in detail over a few of them. So like we talked about the Cartesian product of the field is an example and we're gonna go over it. But often people just take Rn and Cn. So they take F to be R or C. Okay, that's the most natural example. Okay. All right, let's move on. Oh, and also you have a nice subspace structure. So like we talked about, you know, R2 is inside R3, and this guy is a subspace of R3. Is that okay? Does that make sense? So there's a natural ordering for Fn. You can keep taking more and more coordinates, and each one of them is a subspace of the next one. Okay. There's also a cool example where you can now take n to be infinite. So the most common one I've seen is R infinity, and these are all the guys where you have, you know, like infinite sequences of real numbers, like things like binary numbers, right? Like 1 0 0 1 0 0 0 0, or any or the expansion for like pi, right? You know, pi is like this. So if you want to represent it as in a computer, you have like an almost infinite sequence, right? Anyways, so this is also a vector space. You can have infinitely long vector. All right. Okay. All right. And of course, the dimension is infinite. Another standard example we're gonna do in this course are the space of matrices. So I'm gonna go over them in detail for the axioms, but yeah, you can yeah, you can do algebra, linear algebra with these guys. Yeah, and they don't have to be square either. So let me not make them square. Could be like something like this. 1 1 1 0 2 0, something like that. Now, of course, you can order them using like the snake ordering, and this is isomorphic to Rm cross Rn, right? Because you have that many entries. So that's another reason why we have this nice vector space structure. I should write F here. Okay. Okay. All right. Sorry, what are we gonna, yeah, Angela, we're gonna do this in detail, but basically there's a way to send basis to basis. So yeah, we're gonna do this in more detail. I shouldn't go into this. Like for example, complex numbers are isomorphic to R2 because you can write AIB as A comma B. So you can send basis to basis. But this is like way after. We're going to talk about it. Yeah, you're not supposed to know it now. You should just think about it as sending that they're very similar to each other, like geometrically. That's all. Is that okay? Um, just whenever we talk about isomorphic, just think about the complex numbers and R2. But we're gonna go in detail over all these things. Yeah. I shouldn't talk about it too much. Okay, and for subspace, yeah, you can like take this space where you set the first entry to always be 0. And we're going to talk about it, but you can see that this is indeed a subspace because it doesn't matter what the other entries are. This is always becomes, this always stays 0, right? So you're closed under addition, and same thing, you're closed under multiplication, right? This guy is always 0, right? So yeah, so this is a nice subspace for M and M, and here since you can think about the space of matrices as the RMN, where I take each entry to be a component of the vector. All I'm saying here is take this guy to be RMN minus 1, because I remove one of the coordinates. And we already talked about that this is indeed a subspace of RMN. Okay. What do they mean by with entries in the field F? Oh, like for complex, right? So M n of complex, a standard example is like 1 plus I, 3i, ei pi over 4, 6. So you take elements from the field. Here, namely, are the complex numbers. Is that okay, Kellyanne? Yeah, they're independent of each other, yes. Why should some of the entries be 0 and why a? No, it's just, I picked, this is a particular example of a subspace. Yeah, exactly what Meima said, yeah. It could have been any other, it could have been A11, A12. It would have been a different subspace. Is that okay, Ismail? Good. All right. Another example we're going to go over are the set of all functions. So, of course, the standard example is R to R, right? So you have things like this, right? And okay. Okay, but yeah, I will talk about it more after. I didn't add any details here, so we're gonna talk about this soon in the examples. Okay, another example also covered in your book in detail are the space of polynomials. So let's try to understand what this means. So you fix a variable, unknown variable x. So here we never put a number for x, okay? So we always leave it as x. And then here's how you do your algebra stuff. So you have one polynomial, P1 of x, and then another one, Q1 of x. And this could be like, 1 plus 2x. And this guy could be, I don't know, 3x squared plus 5xn, something crazy like that. Or actually, let me make this like this. Yeah. So then you ask how to add them. You add them coefficient wise. So you do 1, you do 2 plus 3, and then you do 5xn. So we add them coefficient wise. Now for real numbers, this one seems tedious, but if you have a field, then we're using the additive structure of the field, right? So suppose, P is, I don't know, some element of the field, like this, and Q is, I don't know, CX and then DX squared, something like that. Then P plus Q will be A0, B0 plus CX and DX squared. And this is indeed a polynomial. This is indeed a polynomial of the field, because B0 plus C is still in the field. So you indeed have a polynomial with coefficients in the field. Pn is a vector space. Here we're doing examples of vector spaces. So again, I'm gonna go in detail over this. This is one of the main examples. But yeah, this is a vector space. Okay, and I talked a little bit about how addition works. Yeah, I mean we're gonna talk about this. Okay. Yeah, and here again, you take your coefficients to be complex numbers or real numbers. Okay. So like 1 plus I, 3ix, ei pi over 4x squared, stuff like that. Okay. All right. So these are the main examples. I list some more that these are the main examples. And then I add some more that we're not going to do in this course, but I just mentioned them. So we have the vector space of k differentiable functions. So, like f prime, f double prime, all the way to fk, they all exist. And when you add two differentiable functions, then if you take the derivative using the sum rule, you get that that their sum is also differentiable. So using the linearity of the derivative, we get a vector space structure. Okay, so that's why this works, because the derivative is linear. If you're doing some other stuff like differential equations, then it's the same idea. If you have some differential operator, yeah, anyways, you get a vector space. Same thing in ordinary differential equations. So this comes up a lot in analysis, but yeah, this is not in our course. All right. Okay, and yeah, you have the smooth functions by taking k infinity, meaning you have all the derivatives. An example is e to the x, right? Okay, all right, so let's start doing our examples, and we're gonna start today and then finish them tomorrow. So let's start with Fn, okay? So again, let's put everything in clear terms. We talked about this, but now let's do it formally. So you have a field F and you take its Cartesian product. So, okay, so you have x1 to xn, and each entry is taken from your underlying field. And the way we define addition here in this vector space is component wise. So, A plus B, V, and C plus D is done component by component. And multiplication is done again component wise. All right. Okay, so that's the one. And why do we have closure under addition and multiplication? So let's talk about that. So you give me two vectors. So x vector is x1 to xn, and xi is in your field, like complex numbers. Same thing. And c1 is a element from your field. Now, since they are done component-wise, you get that you get c1, x1, y1. I should have called it a c. This is complicating stuff. So let me call it c. So you have cx1, y1, cx2, y2, and cxn, yn. So this is what you get, but then why is this in your space? Because each element is in the field, because F is closed under addition and multiplication. Okay, that's all we're using here. We're using the underlying closure of the field. Is that okay? I think that's okay, right? All right, so always this this proofs, and in the homework, always try to go back to your field. So yeah, because this is one of the homeworks, I mean, these are kind of tedious. There's not much content here. Maybe I should do at least commutativity. So this one claims that x hat plus y hat is y hat plus x hat. And how do you do it? Well, you add them component wise. And then you use commutativity of the field at each component. So here we use commutativity of the field, component by component. Okay. So the other ones are the same. You always come back to your components, you do your operations, and then you break it up. Okay, so it's always the same sort of trick. All right. I talked about this a little bit. So we define our additive element to be just a zero vector. So like for complex numbers, we take it to be 0 plus 0 I, 0 plus 0 I, right? So that's our 0 guy. And then when you add them component wise, you get this guys. But then why do you get here? Because again, for the field, we know that this is true for each I. Okay, yeah, I think that's clear stuff. All right. And then, yeah, multiplication, you can get it the same way because it comes into the components. All right. And for additive inverse, we talked about it a little bit before. Since minus xi exists in the field, we can define minus x to be minus x1 all the way to minus xn. So we're vectorizing the additive inverses that we get from the field. It's not more complicated than that. 0v is the zero vector. Yes, Kelly. Is Zn a vector space? Oh, you mean with the Z integers? Yes. Yeah, it is. Yeah, because Z is a field. It's not a field. Am I missing something? Why is it not a field? You have addition, you have multiplication. Product of two integers is an integer. Oh, I see. Right, of course. Yeah, he's right. So you need to use the rationals. Will is correct. Thank you. Hi, Prof. One of the textbook questions has the notation C takeaway R. I'm wondering what. Yeah, we can talk about this at the end. Let me, because that's a good question. I know I did it in the office hours. Okay. All right. Again, all right. So now for matrices, this is also a vector space. And here your addition and multiplication is done entry-wise. GH, whatever. So you have A plus E, B plus F, C plus G, D plus H. Okay. Right. Okay. And why do you have closure? It's the same reason we have closure as we did with the vectors, because you have closure of the field. Okay. All right. Okay, so I see the time is up. So we will continue this tomorrow. I'll stick around for questions. Thank you very much. See you tomorrow. Oh, I see. Yeah, this is right. This is a field. Yeah, so we yeah, it's better to use the notation from the book F3, right? But yeah, you're talking about the modulo numbers. Yes, this is a field.
I had a quick question.
Yes.
We know that if something is a subspace, then we also know that it's a vector space. So like a subspace implies a vector space.
Sorry,
right?
what's your name? Can you say
Or you can just call me Rudy.
Oh, it's Root Rush. Okay.
Yeah,
Okay,
yeah.
go ahead. Yeah.
Yeah, so we know that if something is a subspace, then it's also a vector space. So we know that subspace implies vector space. But is it true the other way around, that a vector space implies that it's a subspace?
So, okay. I think you're overcomplicating it. So we have W is inside V, and we know V is a vector space. The definition of subspace is that W is a vector space. It just happens to be inside some other thing. Like, when you have R3, this is a vector space, right?
Right. Yeah.
But if you want to talk about it with respect to some other space, like R4, then this is also a subspace. But by definition, a subspace is a vector space. Like it has to first be a vector space, and then it happens to be a subspace of R4, but it's also a subspace of R5.
Oh, I see. So they're not related to each other in that way.
Yeah, like I mean, any vector space, like the only one, maybe something like C infinity or something. But even that, you can put it inside quaternions. So for the most part, the interesting vector spaces that I've seen, I mean, they're always a subspace of something else. But anyways, yeah. Is that okay?
Yeah, thank you.
Yeah. So Angela, are you still there? You had a nice question. Okay. Does one imply the other? They're the same thing because it's by definition. Angela, I don't think Angela is here. I don't know. Maybe Angela will watch the recording. So C takeaway R just means take away numbers A plus IB, where you're not allowing B to be 0. So B must not be 0. right? So this is the B equals 0. This is the A equals 0. And you're removing this part where it's only real. Okay. Yeah, go ahead, Perth. You can use the mic if you want.
Thank you. Like I was going through chapter 5 in the book.
Uh-huh.
So like there was this definition, and I'm just literally opening the page right now. There was a definition for like algebraically closed, I believe. So it basically said that you're like a polynomial of degree n, right? So for a field f, it's algebraically closed if that polynomial a n z n all the way to a0, where ai is an element in the field and a n is not 0, has
Mhm.
n roots counted with multiplicity in f.
Right.
But like, how can multiplicity be in f, right? Multiplicity should be a real number.
No, that's not what they mean. No, you overcomplicating it. All it says is like, how should I say it?
Or
Like,
like, is it really like, it's going to be something like
it's
like
still
for,
an integer, huh?
it's still going to be an integer.
Yeah, it's
It's
still
not.
like an integer. It just says,
Uh-huh.
you know, I don't know, like,
I see. Okay, so it's okay. So when you say
yeah,
n
it's still
roots,
an integer. So it just says it would be like, I don't know, like, let's say your guy is
uh-huh,
like lambda
lambda
3 to
minus
the,
3, uh-huh,
yeah, to the 4, and or let's take an element of like a more like a plus I, something like that, right? Then the 3 plus I has multiplicity 4 in the field of complex.
Okay. I see. So that was not exactly. Oh, yeah. That
Yeah.
makes much more sense. Yeah. And the second thing, like, we know that R is a subset of C, right? Uh-huh. We can say that, right? That R is a subset of C.
I mean, like, what's the definition, right? Is A plus IB. And then if I set B equal to 0, what do I get?
Well, yeah, exactly. So that's essentially a real number, right? So
Yeah.
so like in the book, when we're trying to define, we're trying to write a sequence of numbers, right? So like in the questions, essentially, normally you for a complex number, it's a pair of numbers a comma b, right? So for Cn, a general vector will have a comma 0, like a comma a1 comma b1 in a bracket, then a comma, then a a2 comma
No.
b2 in a
You should
bracket.
be very, very careful. Complex numbers are not vectors.
Okay.
Like C is not R2. C is isomorphic to R2, but C is not R2. And that's important because dot product and stuff like that make no sense in complex numbers.
Complex numbers, I see.
But yeah, if you want to take Cartesian product, then yeah, it would be like, you know, Z1 all the way to Zn. And like you said, it would be A1 plus IB1, AN plus IBN.
I see. That makes sense because I think that was question 6 for 5.2, where they did not use the inner brackets. They simply for the inclusion function for converting from Rn to C hat n, they were simply in a bracket. They were like x1 comma 0 comma
Yeah,
x2
so
comma.
this is yeah, you all they're trying to tell you is that they're related, meaning you can represent A plus IB geometrically as the vector of B and A. But please make no mistake, this complex numbers are a number system. They are not vectors.
They're not vectors.
Yeah. Otherwise, like for example, how to make sense of 1 plus I in let's say 3i, 5 plus I, something like that. Like if I have a matrix of complex numbers and you look at them as a vector, then you will have to write 1, 1, 0, 3, 6, 0, and 5, 1, right?
That's true.
But
Yeah.
this is a tensor. This is not a matrix.
Oh, okay.
So now we're doing tensor algebra.
Wow.
So, but that's not what we're doing, right?
Mhm,
We're just looking at this guy as a number system. So
mhm.
number system, and this is R2. These are two different things. So we are looking at C as a number system.
Interesting.
Yeah.
So like field like that comes back to the point that fields are not vectors, right? That's
Yeah, yeah,
yeah.
exactly.
Perfect. Thank you so much. Yeah.
Hi, Prof. Can I ask a question?
Yeah. What's the name?
You can call me Hu Yun.
Kelly?
Hu Yun.
Queen? Okay.
Yeah. So, what's the difference between the component-wise and entry-wise? Like, is the component-wise for the field and entry-wise for the matrix?
Yeah. Yes.
Okay. So, but basically, the computation is almost the same.
Yeah,
Right.
it's almost the same. Like you
Okay.
you have like V1 and you want to add it to like U1 then you add them at the UI. So you have V1 plus U1 and VI plus UI.
Okay.
And then for matrices, you add the like it would be like AIJ plus BIJ, right? If you have two matrices with like
Yeah.
AIJ.
Okay.
Yeah, that's all.
And also like for class V, it's the vector addition, right?
For what? Plus what?
Class V.
Yeah. No, so I didn't get to it today, but it's whatever you get to define the thing, right? Like you get to define, it's not always vector addition because like, oh yeah, we talked about polynomials. Like I'm gonna go over it in detail, but for polynomials, right? If you have two polynomials, we define the addition to be coefficient addition. So we have like, P0 plus Q0, P1 plus Q1x, Pn plus Q1x, and right? So we add their, we do it coefficient wise. So yeah, it changes, but often is just component wise, entry wise. That's the common example, but it can be general. Like here is just coefficient wise.
Okay. And like what's the class W?
I just mean like whatever space you're working with, I call it, like if you're working with W, you equip it with the plus W and C dot W. It's what you equip it with. You equip it with some, like this. You equip it with some operations for this space.
Okay. Okay. Thank you.
Yeah, okay. Yeah, we can, yeah, also for functions, you add them point-wise. Yeah, we'll talk about this. Okay, any other questions? Okay, thank you guys. All right, see you tomorrow.